Alright, should be live. Time for another draftphysics.com, debatephysics.com also. Video presentation, New Year's Eve edition. Yes, I really couldn't give a shit. I just didn't find out till about an hour ago that it was New Year's Eve. Slipped my mind and such. So yes, really don't care about such details. And anyway, and frankly, I'm tired and fed up in a lot of things. So I probably shouldn't even be making the video, but I want to keep in practice. I'm just, still going through the nicotine thing, I guess. I don't know. But, my whole personality is changing. It's a different world without nicotine in my blood. But anyway, I will endeavor to persevere and do my job, so to speak, which apparently is just annoying people. It doesn't seem to, I'm not performing as my instruction manuals would say. This is what I want to accomplish, is persuasion, and I can't seem to get that job done. So anyway, this is back to a Bruce Yearney experiment with wooden blocks, and so I found another version of this, and but it was disappointing because when I really tested it, it was, it says it's 2-to-1, but it isn't 2-to-1. So and even this experiment is a little bit off, so I'll just show it again just for the hell of it. But it's not what you want.
Let's go back to the same mass, but double the rubber bands and see how that affects it.
So it seems simple enough. You double the rubber bands. So when you don't double the rubber bands and you double the weight, well, you do double them and then you double the weight, you get this perfect, exactly the same motion. So indicating that obviously you're conserving the momentum, twice the mass, twice the force, same velocity. And so in this case, you want twice the velocity. But obviously, twice the velocity is asking something from the rubber band. I mean, obviously, the rubber band has to go twice as fast as it was going in the other case. And rubber bands have a finite speed, as you can sort of demonstrate. They don't move all that fast. So as a percentage of that finite maximum speed is all you're going to get. So you could expect that you're going to lose some velocity. And the problem is you can lose a lot. And all the way down to a point where you're saying, you've lost more than half what you should have gained. But anyway, in this case, obviously it's something more than that, but, the experiment could have been done a little bit better. So we'll play this a couple of times just for the hell of it. You should be able to see this, right? Yes. Okay, I could even blow that up a little. And such. The relevant bit. And then I could actually just do it second by second, right?
Mass, but double the rubber bands and see how that affects it.
So the problem here again is if somebody's using their own hands to let them go, it's just not ideal. You want to do the, you want to use some sort of launching device that is quick and it doesn't interfere at all with the experiment in terms of degrading. So you could argue this one was let go later, so this one isn't technically going twice as fast because it got let go sooner than this one did. Something you can definitely make those kind of arguments, and it all happened so quickly that who knows, but this one you can't do frame rates on. Obviously it's way too fast to get anything useful out of it, but I did anyway, and it was like 10 and 6. So instead of 10 and 5, it was 10 and 6. So it wasn't quite twice the speed. And alright, so we'll go back to regular speed, and I think it plays it in slow motion here. Alright, so he's trying to let go of the one in the foreground. So the one in the foreground, this one did move a tiny bit, but he obviously hasn't let go of it yet. The other one, so this one, it's hard to say. That one's moving now too. So maybe they gotta let go at the same time. So it's very close. Yeah, it's very close. So this takes 1,000,000 frames actually, and so it's it was way too many frames to be worth, and there's way too many dead frames. Blah 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 blah. But it seemed close to okay. 1 to 1.6. Yeah, so it was 1 point. It was instead of 1.4, it was 1.6. So it was clearly faster than 1.4. So that's all you can say. But it wasn't anywhere near 2. All right, that one. So then this case was a little bit better, but this one seemed almost obviously more flawed. So I mean, this is why these experiments need to be done. You know, people complain, yeah, you got to really do these experiments well. I mean, doing them cheap and on the cheap, it's just not good enough. They deserve to be done well. And it's really a tiny margin between, you know, results can be fudged so easily. You don't have to do much to really screw around with what the outcome will turn out to be. Alright, so this is like a handheld camera, you know, somebody's holding the stick, and so it's way below perfect, but this one was a lot closer to 2 to 1. So it's just, again, you can just manufacture the outcome, and you know, that's just not good enough. So yeah, it seems obvious this one was let go first. Seems obvious to me. So obviously it hits way ahead of the other one. So you know, not much you can say. I mean, obviously it comes out my way, so that's good. But it's coming out my way not for the best of reasons. So you know, it's just, I guess part of the why I hold them at different positions. They should hold them, you know, the same way and release their hands the same way. And you know, that would be better, but whatever. It should show up here soon. You can see that, right? Almost. Yeah, let me move it this way. Alright, you should see that one of them gets released a little bit earlier. Yeah, you should see that. Yeah. There we go. Alright, so the one in the this one, it's definitely moving. This one isn't moving yet. So, and then his hand's back on it again. So yeah, it moved and it didn't move. So yeah, I don't know. It's like a false start. So I guess it didn't lose anything or gain anything. So it moved a little, but then it stopped. Let's see if it actually goes somewhere here. Come on. Oh, I have to be back in this video. There it goes. So yeah, it's definitely released sooner than the other one. So it spoils a very good outcome for my side. Yeah, very good outcome for my side. Yep. All right. So yeah. So you know, you can't. It's just not good enough. Gotta get better experiments than this. And yeah, nobody's willing to do them. So millions of scientists on Earth, and none of them are interested enough to nail this stuff down. Just like they, you know, never did the Eddington experiment from space, never even tried it. We're supposed to believe. I mean, you know, seems so incredible to me. I haven't heard nobody will provide me with a paragraph of text explaining exactly why a scientist would say, no, don't bother doing that. I mean, if it was proposed, like, oh, we're going to take 5 minutes of satellite time and do the Eddington experiment, who would object? I mean, why would they object? Why would they say, no, let's not bother? I mean, again, as experiments go, it's as cheap as you can get, and it's one of the most famous experiments, and you get the added value where you can produce some real visual evidence. You know, stuff that you could actually, you know, show on TV. You know, that you could actually make, instead of showing simulations, you could actually show real evidence of real lensing. I mean, why wouldn't you want that real evidence? Instead of keeping drawing it and showing this fake crap, why wouldn't they want real hard, straightforward visual evidence? And there's no good reason. I mean, you can't. What am I supposed to make up as a reason? Why would a real defender of science say, "Nah, I don't think they should do the experiment from space"? It's not a viable experiment. It's not a useful experiment. Not a good experiment. Of course, it's a good experiment. It's a brilliant experiment to do from space. You just can't make any sense out of that kind. So those kind of obstacles just sit there in front of me and say, none of these people can be honest players here, because no reasonable science liker, especially not a science lover, could say, don't bother doing the experiments. They just couldn't do that. They couldn't say those words. All right. So I know I have a Alcohari video. We'll do that. Yeah, we'll do that later. Oh, soon. We'll do that soon. Yeah, I gotta make that smaller. So he just babbles on and on about quantum mechanics, and he does such a poor job of it this time. Like, so without his script writers, just winging it on his own, without making a TV show, a YouTube show, whatever you want to call those documentaries it did. It's just babble. I mean, it's almost to the point of being completely incoherent. And it's just kind of a funny defense of quantum mechanics, because he basically makes it sound like it is all just bullshit, because he can't explain any of it in any rational terms. So, I guess that's what we will go to, since I can't find anything else to go to. So yeah, I have just looked around over and over, looked for these, see if I can find some of these basic experiments, and just can't find anybody who's done any of these basic experiments. And it's just really irritating, especially done them well. All right. So let me just play this crap. I've been quantum mechanics my whole life, and I've been full of shit for my whole life.
Mechanics. I've been obsessed with quantum mechanics myself for over 4 decades. In fact, the first Friday evening discourse I gave was 21 years ago on quantum mechanics. It was about a year after I had published a book on the subject, Quantum, A Guide for the Perplexed. I always tell people who read this, I say, I can't promise that you will be any less perplexed when you read the book. You'll just understand why you're perplexed.
It doesn't even make any sense. What does that even mean? If I understand why I'm perplexed, then I wouldn't be perplexed. So this is just gibberish. But yeah, they have this incomprehensible theory of mush that just converts all the simplicity that Galileo, Descartes, and Newton provided, this nice foundation of understanding the universe as this thermodynamic system where all the energy is still in the system. It just transfers from one object to another object. And you have to consider that the forces are objects. They're transferring their capacity, their motion, to the things they interact with, and that's not much of a reach. There's, even wind is invisible to us, and but it hits you, and you know what it is. It's made out of something, and it's just going to transfer its energy. It's not going to keep its energy. You're going to take its energy. Trees absorb wind. Tornadoes get tired. When they hit a bunch of trees, it steals their energy.
In fact, on the back cover of the book is the famous quote by the great Danish physicist Niels Bohr, who says, if you're not astonished by quantum mechanics, then clearly you haven't understood it.
So again, this is the basis of their understanding of the essence of the universe, the fundamental essence of the universe they're claiming is beyond our comprehension, that it's so ridiculously convoluted and silly that we can't understand it. that sounds like the premises of religious folk, not scientific folk. I think people say, it's like even when you could make arguments against evolution years ago, people would say, well, there's no missing links. And it's a pretty good argument, okay, if you have drawn some wrong assumptions about how evolution works. That is, if you think big giant populations evolve, that some one little person inside of a group of 1 million changes, and that he changes everybody else, when no, he just gets diluted out of existence. And it's little populations that do all the evolving. So once you understand that it's the isolated population, the one that gets separated by a river or a volcano or some event, the ones that walk around the continent and end up going to South America and becoming Eskimos and all that, those are the people who do the evolving, are those small populations. That's why there's no missing links, is because it's very small, isolated populations that do all the evolution, the substance of it. They make the weapon, and then once the better version has been created, it expands and then defeats the majority when it is big enough to defeat it.
Now, what I want to do in this lecture is several things. I want to give you an outline, a brief history of the subject, why it is so perplexing and so weird.
So you're going to go back and do the same thing you did 25 years ago, except you won't succeed any better now than you did then. Great.
But also, why it's the most powerful.
All right, so there's not going to be any evidence of this power, that this theory does a damn thing, and it's all these exaggerations that somehow it invented the cell phone, and it invented computers, and it invented, it didn't do any of that. So those are all preposterous exaggerations. You didn't have to believe in entanglement. You didn't have to believe in superposition. You didn't have to believe in black holes. You didn't have to believe in big bangs. You didn't have to believe in dark matter. You didn't have to believe in dark energy. You didn't have to believe in positrons. You didn't have to believe in neutrinos. You didn't have to believe in any of that crap, okay, to have been at the birth of the integrated circuit.
Theory in the whole of science. In fact, I should correct that. Quantum mechanics isn't a theory.
Okay, so this is where they really go off the rails, because they don't predict anything real. They have one experiment, this silly thing with muons and a giant magnet. Now, I have to find out exactly what this silly experiment does. I can't, you can't see the actual data it actually creates, right? And apparently this is the silly experiment that they keep doing this, to higher and higher accuracy. And it's you're just saying, what is this crap? Predicting the magnetic moment of a muon? It's ridiculously obtuse nonsense. So that's all they do, is this one experiment. They have an experiment, and then they have a predicting machine, some sort of stick, with a Vogelkugel on it that they spin, and that predicts what the other machine is going to produce as an outcome or something. It's just ridiculously convoluted nonsense. It doesn't have anything to do with some sort of success. This is not the definition of success. This convoluted circular logic is not the definition of success. They're throwing the anvil thing. They're throwing the shot put, and then they're out there moving the target and then saying, look, it landed right on the target. That's all they're doing. Okay, that's how they're winning their gold medal.
Quantum mechanics is a framework for a mathematical framework.
So there's no frame, okay, and there's no work. So that's the real point, right? So it's like their claim that it takes 25 times the fuel to go 5 times as fast, and then if you're spinning something 5 times as fast, it'll do 25 times the work. There's no evidence that that happens. It doesn't happen in the turbines in Niagara Falls. I can't make them. If I spin them 3 times faster, they're not going to make 9 times the electricity. None of that crap's ever going to happen. So this theory is all nonsense, okay? And it's all based on that kind of hyperbole, all that kind of just insane exaggeration about what functional work this theory has ever done. It's never done any work ever.
for understanding the workings of the microcosm, the subatomic.
So it doesn't do anything to understand anything because it's all frankly wrong. Electrons don't orbit, nucleuses. There are magnetic monopoles. They're called electrons and protons. Magnetism and electricity are just two versions of the same circumstance, and two ways that the arrangement of electrons and protons can express themselves. When you're moving electrons and protons, that's electricity. When they have positions where they're polarized, that's magnetism. Not that complicated, but they've turned it into absolute convoluted mush.
World, the world of atoms and beyond.
Beyond what? You mean electrons and protons? Oh, and then they say they've got all these 400 other particles, and nobody can explain where they are. How do they arrange themselves in the atoms? Where are the neutrinos hiding? Where are the positrons hiding? Where are they now? Where are all the positrons? Where could they possibly be hiding?
The same way that classical Newtonian mechanics isn't a theory.
Okay, so there's no point in saying this stuff because you're directly refuting it. So they're refuting Archimedes. Okay, they're saying the law of the lever doesn't happen, isn't true. That this thing called kinetic energy is conserved, and no momentum, you can make free momentum all you want. That's their new physics. But they have no regard for any of those classic physics. It's none of that thing they call classic physics is classic. They don't consider it classic until it's Leibnizian. Until Huygens and Leibniz. That's what they're calling classic physics, not Newton and Descartes and Galileo.
Again, that's a framework for understanding the workings of our everyday world, forces and momentum and energy and so on. Quantum mechanics is its equivalent down at the micro scale. And it's very different. It's very counterintuitive.
So more of this, that makes any sense anyway. And we're not asking for it to be intuitive. It just has to be rational. I mean, you can't say something is two different things. You can't say it's up and it's down. I mean, this is the baby talk of it. And it's just ridiculous. You broke all continuity rules. You can't say something's on and it's off.
And yet it's powerful and it's successful.
So powerful, doing nothing in the real world. So it hasn't done a single real world thing. It's only done something in their weird standard model construction bullshit. But in any way of actually creating an event, it hasn't created any event in the world that has done any human being the least bit of good.
And we've built our modern world on it.
So you haven't built it on that. That's just a lie. It's just engineering. Everybody knows it's just engineering. If it was theory, they would just pop the blue LED. It wouldn't have taken 20 years. So obviously it's not about the theory. It's about the engineering.
So I want to start first with a little bit of history. I don't want to go... I've got 1 hour to cover a lot of stuff. So I'm going to whiz through a bit of the history. But I guess for many of you, if you know something about quantum...
So it really is just, this is how the whole thing is just like he put this together in a half an hour. It's just so bad.
Mechanics, then you probably know some of these names, some of the great quantum pioneers, going back before 1925. In fact, the original quantum theory, the original seed of the idea began in the year 1900, thanks to another German physicist, Max Planck. Planck suggested that radiation given off by warm bodies isn't continuous, like the stream of water from a tap, but if you look...
So the stream of water from a tap is not continuous. It's, again, molecules. An amount of molecules rolls out of the tap. It's made out of discrete bits. So again, they can't come up with any analogy for this, whatever it is, like their scalar energy, these magical forms or magical events, because they don't happen anywhere. There's nothing you can compare it to, this flowing without some sort of discrete medium that's flowing. There's no such analogy.
Carefully enough, it's discrete. It comes in lumps, like separate drips.
Yeah, that's what it all does. That's everything comes in lumps, separate drips. That's the whole point of Newtonian physics, in a sense, is that everything is just things and events.
A few years later, Einstein extended that idea and said that actually all electromagnetic radiation, light, in all its wavelengths, ultimately can also be thought of quanta particles of light, which we now call photons.
So, and again, whether he called the quanta, the energy quanta, the photon, whether he didn't think that the photon was a thing. He thought the photon was made out of bits of energy, I believe. So again, it's this, but even if he didn't, the real viable idea is that, yes, a photon is a ridiculous concept, something that's this, 5 miles long, a blob 5 miles long, or 5 trillionths of a second, an indescribably small amount of space it could take up. The frequency argument just makes it implausible. And what this really is like Morse code. It's a frequency. It's bits, dot, 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 separated by a distance. It's dots separated by a distance, a period. And it makes perfectly good sense to understand, well, that's got to be the better default explanation for a photon, that the frequency is the fact that it comes in clumps at a distance. That creates your frequency. It makes so much more sense than trying to imagine some object, some singular object that can be 10 miles long, or whatever the, some sort of, or what do they measure photons in? Oh man, yeah, the way words disappear, nanometers. So from nanometers to miles. You can't make a jellyfish that's 1 nanometer and then a jellyfish that's 10 miles. But it's easy to understand the separation being in those units at the speed of light.
Physicists got interested, got involved. Niels Bohr himself, the Danish physicist, extended the idea to describe the energy of atoms, or more correctly, the energy of electrons as they arrange themselves around the atomic nucleus. This was very soon after.
So arrange themselves, blah blah blah. Now, obviously, I would argue the arrangement is being necessitated by the fact that everything in the universe is under pressure and it's all being jiggled about, and that's why it can't just collapse. Is because there's just too much jiggling. Everything's just moving a little bit too much chaos for it to all fall into place.
Ernest Rutherford had.
So Rutherford had the better idea in the sense that they called it whatever, the plum pudding version of the atom. But the idea is that the nucleus had electrons and protons in it, and and it's just so obvious that the neutron is just such a perfect candidate for understanding that a neutron from a distance, an electron and a proton stuck together, would look neutral from a distance. It would look purple. Say if it was blue and red, you would look and see it at a distance, it would look purple. And so, yes, it could be called something like a neutron because it would look neutral. But as you got closer to it, you could understand, it has an equal amount of both charges. That's why it's neutral. It isn't because it has no charge. It's because it has 1 unit of each charge. And that means that now you have a 2-to-1 relationship of electrons to protons in the nucleus. The nucleus has twice as many protons as electrons, and therefore the exterior is where the rest of the electrons are, to even out the fact that there's the same number of electrons and protons in the universe, ultimately, which makes some intuitive sense, obviously.
Given us the very first inkling of what an atom looks like. mostly empty space, a tiny dense nucleus in the middle with electrons around the outside. That was a picture of the atom that looked like a miniature solar system.
So it really didn't have to look like a miniature solar system. It could have looked like any kind of geometric object, which would have been the sensible understanding that there's only 100 of these things. And at the time, whatever they knew in the 20s, I mean, they were starting to develop, so they knew there was, going to be less than 100 of these things. And it's just geometry, and you're just building on the geometry of the first. So the hydrogen becomes the core of the lithium, and then the lithium becomes the core for the carbon. They're all building on top of each other.
Which we soon discovered wasn't really quite correct. But the idea, this quantum theory, the idea of things are quantized, the energy of the electrons around the atom also comes in discrete.
So there's no energy innately in the atom, okay, besides the fact that you could say there's energy between magnets. So these are magnets holding these things together, and they're going to hold them in these positions, and some better than others. These won't pull apart at all, but this one comes off really easy, right? So it just depends on the arrangement and the orientation, whether or not, how strong or weak, whatever you want to call their energy is. And the real point you're arguing is how fast would they move if they move from one position to another geometric position in an atom. And it's that velocity that creates the message the object sends. So when an electron moves and it's in this field of energy, it pushes on the little bits of photon, and it expands or contracts the frequency based on moving towards it or moving away from it. If it moves away from it, it expands the frequency. If it moves towards, it compresses the frequency. And so those are the signals sent, and the real way the energy is transferred from one electron to another. How the system transfers energy is through those interactions.
Levels, discrete values. Electrons couldn't have any energy they wanted. Others, like the Frenchman Louis de Broglie, talked about waves behaving.
So this was the biggest second disaster in physics was the de Broglie mess made of creating this whole notion that electrons wave and then antimatter and all this other nonsense. Pauli with the antimatter, just nonsense.
Like particles behave like waves. Things were starting to get a bit weird. You had people like Max Born, another German physicist, Wolfgang Pauli.
Yeah, and these are just compromisers. Okay, yeah.
Pauli,
try to find some way to mix things that should never have been, that weren't the truth in the first place. So yeah, try to make a new letter out of two letters that aren't even in the alphabet.
The British physicist Paul Dirac. What we're celebrating this year, as International Year of Quantum Science and Technology, is...
I'm glad that year's almost over. Yay! Oh, it is pathetic.
100 years since the invention of the full quantum mechanics as it evolved from the old quantum theory, which is due...
So they're saying that quantum mechanics is 25, it was 1925. Well, says you, frankly.
So not just Heisenberg, but an Austrian physicist, Schrödinger, he of the famous cat in the box that's dead and alive at the same time. More of that later.
Right. So the guy who had to keep telling people that electrons can't think, and they can't hide from you, and the moon doesn't disappear, and yes, cats aren't alive and dead. It's too ridiculous. So the guy kept trying to keep you people rational, and you just refused to listen. So it's pretty bad when they bring up Schrödinger as part of quantum mechanics, because he really did oppose just about everything physicists did to it.
Heisenberg and Schrödinger both developed mathematical approaches to understand the atomic world, but rather...
Yeah, I'm sorry, they didn't... Heisenberg didn't say anything. He just made an assertion. Somehow, magically, you can't look at an electron, even if you have a capacity to look at it. That is, even if there is some mechanism we could use to see it, we still couldn't see it because it doesn't have a place and it's not in a place, because he says so. So that was rather ridiculous. And obviously these are very tiny things, and obviously we aren't going to be able to see them without interfering with them. So, duh. That's just okay, yeah, everybody can accept that. But it's not a law. It's just a fact of, unfortunately, of the reality that there's nothing to take a picture with. There's no discrete enough mechanism to hit an electron with where you can define its location without changing its location.
Different in their approach. But it was soon discovered that they were actually equivalent.
So whatever that could possibly mean, obviously, equivalent. There's no equivalence. And Schrodinger's equation, I still can't figure out what it even means as an equation. It basically says if you have all knowledge, you can answer lots of questions. But if you don't have knowledge of everything, you can't answer any questions. Yeah, duh. So yes, if I can't figure out where it is, I can't know what it's doing, I can't figure out where it's going to be. Yeah, that's right.
Today, when we talk about quantum mechanics, when we teach quantum mechanics to students, we use a mixture of both.
The worst frickin'...
Okay, whatever this commercial is. Oh, I can't skip it. Well, I guess I can. I'll just wait for it, right? It should bring up a skip, right? Do I have to play it to skip it? Yeah, I probably do.
State to live in right now is New Jersey, and nobody's talking about it.
Quantum mechanics culminated in this famous conference, the 5th Solvay conference on...
So that's I think they colorized this photo, right? So I don't think that's the original photo. But anyways, it deserves colorization. But again, this is the story, is these people got to tell everybody else what they should believe. So this is all the people in the world who get to tell us exactly what the truth is. So this is the grand poobahs of the quantum religion. And, that's just pathetic that the world is just that controlled by this, old farty, nerdy club of wooists.
Physics held in Brussels in 1927. Very often, this photograph is regarded as the most intelligent picture ever taken. Now, the physicists among you might enjoy, and no doubt have done in the past, try to figure out who all these great names are. Of course, everyone recognizes Einstein in the front row. Marie Curie, the only woman in the whole photograph. However, she has something over the rest of them. She won 2 Nobel Prizes. None of them managed that. But of course, you have Henrik Lorentz, look, there's Niels Bohr. Niels Bohr at this point is only in the secondary. He's not even one of the grandees yet. But then you get the young guns, Heisenberg and Pauli and Schrödinger. Anyone who is anyone working in this new theory.
So this is like, what a waste of time, right? I mean, this whole... Look at the authorities. They're all kind of balding and stuff, so they must know what they're talking about. Blah, 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 blah. I don't know. What does it mean? Nothing, frankly.
The theory of the atomic world was at that conference. And often the way history is taught, it's suggested that quantum mechanics was complete. It was finished. They'd sorted it all out. Now let's go and use it to understand physics and chemistry and build the modern world. By this time. Famously, the 1927...
That doesn't make any sense. Obviously, it was still... They hadn't answered any of the questions that really need answering. But whatever. Blah, blah, blah.
Solvay conference was also a time when the 2 giants of the field, namely Einstein and Niels Bohr, had their famous debate about the nature of reality.
At this time, Einstein was saying things like you'd never be able to build a nuclear bomb, and... so they were both saying lots of stuff that just wasn't true.
And simplified versions of history would say, well, look, Bohr won the argument. Bohr had his famous institute in Copenhagen, and his view, together with his
So again, yes. So they had the majority somehow, and so he won the argument by the fact that he had a majority, but not because he made a salient counter argument. So the fact is that the arguments made were valid arguments against quantum mechanics because it had these silly, issues of allowing objects to somehow carry information regarding how something else is, what's going to happen to something else if it does what it does, this whole entanglement argument. And it's intractable. It just makes a mess out of reality.
Group of young geniuses, Heisenberg and Pauli, created what we today call the Copenhagen picture, which is a view of reality they argued was forced upon us by the mathematics, by the theory, and by experimental evidence, which suggested that...
So all of that comes down to the stupid two-slit experiment and this silly wavy crap and this idea that somehow a photon interferes with itself. And it's all just kind of just so idiotic that everybody should be saying, no, there's got to be a better answer than that. And the simple answer is just so obvious. I mean, it's just an aperture, and you're making it smaller and smaller. And what happens as you make it smaller and smaller is you increase the likelihood that the photon is going to interact with the surface. The smaller make the aperture, right? Big, lots of photons to get through, no problem. The smaller I make it, the fewer photons get through, and the ones that do get through interfere with the surface more likely. So again, it's just so obvious this is a surface phenomenon, and they've turned it into this whole wooey fable. And it's just that. It's just a wooey fable. A silly wooey fable. All right, let's see if we have any commentors. It's forced reality. Good, so you don't think much of the New Year's either. Very pretentious to deny that the mechanics of the universe can't be understood, especially what is happening in the small universe. Well, it has to be simpler. That's the part that's so irritating. And that's the part that's just unscientific, right? I mean, you have to be a non-believer in evolution, right? Because that's how everything evolves, right? You start off with simple chemicals. The simple chemicals become complex chemicals. You can't go the other way around. The complex chemicals don't become simple ones, right? I mean, human beings aren't going to evolve into green slime. It ain't going to work that way. And the very fact that physics is giving all of these little things these extraordinary functions, it just doesn't make any sense. How can the little things have functions we can't do? I can't do this and this. How come a photon can do all that crap when I can't do it? Too ridiculous. What's happening with electrons and protons can be explained and understood. Yes, certainly it can be, and it's necessary to understand their function because they're the ones that do create charge. We know they create charge, and I think it's obviously they create magnetism. I don't know how people can't understand that, yes, the electrons and protons are creating magnetism. So, maybe you don't want to use the word magnetic monopole, but frankly, that's what they are. They got to be. They got to be creating it. So it's the same function. It's the same mechanism. It's made out of the same thing. Charge and magnetism are made out of the same thing, which is the idea you can create poles. Polarity. All right. Hey, have you seen my email? Yes, well, you're kind of obsessive, frankly. Yes, I responded to your email. I sent you an email saying, yes, fine. Friday. Okay, jeez. All right, the Schrodinger cat thing has driven me nuts for so long. It's a huge red flag that you're talking to a quack. Let's see. So, I don't know. The Schrodinger cat thing has been driving me nuts for so long. It's a huge red flag that you're talking to a quack. I don't understand what you're saying. It's clear that the Schrodinger was mocking quantum mechanics. That was his intent in creating the thought experiment, is to prove, to demonstrate that there's no viability to this concept in physics because the cat can't possibly be physically dead and alive. So I don't know your point. So you're going to have to say more than that sentence because you're not explaining what you think Schrodinger cat demonstrates. Let's see. Quantum mechanics made a mess with what physics should be about. Well, yeah, it's a distraction. It's a religion. So they turned something that was getting very mechanical. I'm just saying all of these physics was getting really mechanical, and Leibniz didn't like that. That's part of this truth. And I don't think Huygens liked it. And certainly Euler didn't like it. I mean, he was another religious nut. So the guy who formulated most of the mathematics that were the precursor for Einstein's math, all of these guys were religious kooks first, and they didn't want a mechanical universe as the answer, right? Because that turned them into robots, and that means determinism is true, and that means it's, we're all just, garbage in, garbage out machines. Okay. Yes, New Year's is really stupid. Celebrating what? Yeah, more problems. Yeah, just another chance to be, to roll your dice with this skull and crossbones on it. Maybe this will be the year you are killed. Yeah, good luck with that. Okay, yeah, it's more terrifying than, optimistic. Anyway, especially the bigger picture of what another year means. Yes, exactly. Especially when you're in long of broken tooth. Yeah. So anyway, Copenhagen opened the door to a indeterministic way of viewing the universe. Well, I mean, clearly that's what Feynman turned it into. So Feynman was the big random thing, and I don't know if that's exactly Copenhagen, but but yeah, I mean, it's still the very idea of just claiming that, like I said, that the photons are interfering with themselves in some superposition is just, you've just destroyed all kinds of mechanics. When it's deterministic down to the most elemental interaction. Well, I mean, it is by their own definition. By their own definition, they can take a piece of cesium or some other material, and they can excite it, okay, with microwaves, and they can measure a bajillion little tiny oscillations. Exactly, and they'll do exactly the same number of oscillations in each second. Trillions of these little oscillations. So something that precise, they're pretending is all doing all of this wooey entanglement crap. I mean, it's just so contradictory. All right, so DJ says, I'm saying that people who take Schrodinger's critique as if it's what he believed to be true obviously haven't spent even a moment looking into the subject. Well, I'm just saying, obviously they all are cheating. All the physicists are cheating the argument entirely, yes, because they're implying that it is like Schrodinger's cat, that Schrodinger was right, that the cat is dead and alive, that's a perfectly rational explanation for the circumstance, that if we're not looking, if nobody's taking pictures of the cat, if we don't have a video camera in the box, the cat can be all kinds of things. It can be going to Venus. How do we know? Because the quantum world is so magical that it's they actually think that a photon coming out of the double slit could go to Venus. I mean, they think it's a real possibility. And it's just so ridiculous that they get away with that crap. So yes, I sort of got the idea you were making that point, but I mean, it is impossible for the casual viewer to know it because these physicists never say that, they never tell you the truth. They never say this thought experiment was created to mock quantum mechanics, not to make it understandable. It was being used to make it so you would know it can't be the truth because it's too ridiculous an answer. And yes, they don't tell anybody that truth. That the whole point was to illustrate how silly the theory is.
The atomic world wasn't something that we could picture. We couldn't talk about an atom as a miniature solar system with electrons buzzing around.
Yes, we could. So that's the part that's just so funny. We got there, and we threw it all away, and that's just so sad that they had all the pieces and they threw them all away to go for all this woolly, vaporous, made-up crap, instead of just sticking with the pieces that really worked. I mean, they were really good pieces. The electron and the proton were really good pieces. I mean, that's your elemental charge. You can't get more important than that, because now you can make dipoles, and now you can make tripoles and xipoles and comply, so all kinds of poles.
You couldn't even imagine what an atom was like. It was maths. It was abstract.
So that, I know, again, as a kid, certainly growing up in the 50s, it wasn't hard to imagine, for me, frankly, once you understood that you had these things called positives and negatives, and you just understand that they work like magnets.
What quantum mechanics could give you, they argued, was predictions about the results of measurements if you...
Okay, so we know that these predictions about measurements is all hype, that nobody does any of this. There is no examples of anybody doing all this math, predicting something, and then showing us the experiment where the prediction worked. So where's the example? Where can I go on YouTube to find somebody who calculates a Schrodinger equation and then predicts an outcome somewhere for something other than like rolling dice? Some answer we already know that's randomized enough. There's already so many random that there's no way to predict. But they can't even predict the fact that if I reduce the capacity for there to be a random outcome, that is, I drop the dice on, some sort of balloon or padded object, that I would change the probability, just like they figured out when they did lottery numbers, right? And we had machines that would do the lottery number. Well, they found out some of these machines were, if you put the numbers in all in the same order in the same way, that you actually did not randomize enough. And you'd have patterns that were created. So their physics can't even predict that. If I asked them to tell me, will this machine create enough randomness to break any static correlation that might exist between the rows, where they are placed in the machine before they go into the machine, any correlation to the outcome, they can't predict any of that with their math. So they keep claiming their math is doing something, and there's no evidence it does a damn thing that you couldn't do just looking at it and saying, okay, there's 35 numbers on this roulette wheel. Okay, you're gonna create an event that has so many variables in it that it's going to be synthetically random, and all I'm going to do is predict the fact that, well, unless you have two 13s on there, all the numbers are going to have the same probability of showing up.
If you were to look, and so, well, if you look to see what an atom is doing, or
so there's more bullshit about what a look is again. So again, we all know there's cell phone calls looking at you right now. You're getting looked at. You're probably getting looked at by some. There is some energy that probably is bouncing off of Pluto. When it comes back. I'm trying to think of how what kind of echo energy we could be getting hit by. So you could be getting hit by some energy that actually is 100 years old. It went past the Kuiper belt or went past some stupid thing and has bounced around a few times, and now it's coming back again. But there's all kinds of energy you're getting hit by. All the stars are sending little photons. You're constantly getting bombarded by energy, and we're supposed to pretend that somehow the universe isn't constantly taking a picture of you, that somehow your physical electrons and protons know the difference between a flash bulb, taking a picture on purpose, and all that other photons hitting them. Somehow they know the difference. No, they don't know. They don't know the difference. They can't hide from the whole universe, and they can't hide from you. And so it's just a ridiculous idea that somehow there's something called measuring. There isn't. Everything is measured constantly. It can never escape being measured. Every single atom is under intense pressure. I hate to say the word, there's a zillion, okay, little things flying into the atom constantly, hitting it. It's under constant pressure, this photonic pressure. And that makes any notion of entangle and de-entangle nonsense. You can never escape the universe's X-ray camera. It's always on, and it's always taking your picture of every single bit of you is being photographed all the time.
Where an electron is, then this is what quantum mechanics tells you will find. And sure enough, that's what they found.
Oh, what a lie. So, I mean, just this storytelling. Oh, yes, we predicted lots of things. We predicted that you didn't predict the shuttle blowing up. You didn't predict nothing. I mean, people actually did predict that in the sense that they, they said the number would be about 70 or 75, that every 75 launches you'd have a catastrophic failure, and it turned out to be about right. See if we got any new comments. Let's see. All right, let's see. Copenhagen open the door. Okay, and fixed position electrons in proton geometry should be the only accepted way of viewing the material universe and particles that blink in and out of existence. Ooh. Only way of viewing the material universe and particles that blink in and out of existence. Higgs boson should never have been taken. Obviously, it should never have been thought of as a, is this a viable? I mean, this horseshit that they can make particles out of photons. I mean, they've gone so crazy in so many ways that they just ruined they've ruined physics. They just turned it into some silly, they don't even understand their own thermodynamics anymore. The very fact they can't figure out that gravity is creating energy in the sense that it causes things to have momentum and crash into the earth. And so you'd have to concede that it's creating free thermodynamic energy in the universe. All right, so you can't be running out of energy if gravitational bodies keep making energy. And obviously I would argue that's exactly what's taking place, that's the engine of the universe, is the contraction, it will eventually, okay, that's how you store the energy, and then you release it by expansion. So there's an equal amount of contraction happening at the same time their expansion is happening. So you don't have an entropy problem, because the universe is contracting just as much as it's expanding. They just broke everything.
And quantum mechanics explains so many.
Okay, so he says, I'll just say this is so horrible that they say it explains so many things. Explains nothing. Not a single thing does it ever explain. You can't write quantum mechanics explained it on the bottom of anything. It doesn't explain anything.
Experimental results, which until then people hadn't been able to figure out.
We know the experimental results are what they've perverted them into. So they call it a double slit experiment when there's no slits. They call Stern-Gerlach when they're shooting silver atoms, and they call that measuring the spin of an electron. I mean, they're just preposterous in how they lie about what the experiments, a rational interpretation of any of these experiments. They can't rationally describe or honestly describe a single experiment. They can't even draw a picture of the outcomes. So they'll tell you, they'll draw these squiggly lines and say, that's what photons, and it's absolute nonsense. There's a very specific pattern created by these slit experiments, and they ignore the very specific pattern.
It turned out quantum mechanics got it right.
Yeah.
But at its heart, there was this mystery about, really? Can we really not understand what's really going? Can we not have a picture? Einstein famously said, if everything ultimately is made of quantum particles, then is the moon not there when I'm not looking? Do I only...
Right. So he is also mocking it, and it's a perfectly rational mock to argue, what are you talking? What's this measurement thing? Well, how does it matter whether my eyes are receiving the photons or the photons hit a brick wall? How does the object know whether I saw it or a brick wall saw it? I said no. It can't know the difference. So why are we having this conversation that the moon could give a crap whether I see it or the wall sees it? It couldn't give a crap. Duh. And somehow these mush talkers overcame all of that mockery and sustained this wooey, silly theory.
Bring it into existence when I observe it, as you're telling me happens when I observe atoms. Well, people working in quantum mechanics, that's philosophy.
So you're not going to pretend. Well, yeah, that's a good argument. So hell with that. We won't. We'll just say, okay, we'll call that some name. But obviously they don't have a response. Or they don't have any way to rationally respond, except to run away.
Right. Let's get on with things.
Yeah, let's just do more of our perfect predicting of absolutely nothing and just talking about how we solved every problem mankind has ever known with our super QM, and we never did a damn thing with it. We couldn't even, we can't pour it in the gas tank of a mini bike and, drive to the grocery store. There's nothing they can do with this frickin' crap, this silly theory. It doesn't do anything useful.
And they did. If you think about the progression of quantum mechanics throughout the 20th century, we start with the old...
So this will be the funny part. Yeah, we'll start with this silly diagram. We made this silly drawing of the universe, and then we did this silly drawing, and then we did this other silly drawing. Oh, yeah, that's right. That's all we did for the last 70 years is a bunch of silly drawings. We didn't solve any real problems.
Quantum theory of 1900. By the 1920s, we have fully fledged quantum mechanics. By the late 20s, people like Paul Dirac were already developing advances on quantum mechanics, saying, well, the other big theory in physics is relativity theory. So special relativity, the idea that nothing can go faster.
Yeah, well, we still didn't have a car called the quantum, did we? So I hadn't really caught on yet.
Than light, E equals mc squared, and all that business. Time is the fourth dimension. People like Paul Dirac started to connect that with quantum mechanics. And we get the early ideas in what's called quantum field theory. That develops by the 1940s. People like the great American physicist Richard Feynman, together with Schwinger and Tomonaga, they develop what's called quantum electrodynamics.
Right, so that's the one I got to figure out, the Schwinger other guys. So all of a sudden these three guys all invented the same thing at the same time. I say bullshit to that. But this has to do with this silly... It's either the electron scatter experiment or it's the muon magnetic moment experiment. But I think, and the device is called a magnetron or something. I don't know what it's called. But yeah, I got to do some research on that. Because I got to find out what this hype is. What the fuck are they talking about? What was this great insight? I can't find anything that makes it rational.
Which is quantum mechanics applied to all matter and all electromagnetic radiation, light and stuff, how they interact together, their properties. Quantum electrodynamics is often regarded as the most accurate.
So again, more talk. Okay, regarded. But proven by what? Where have you proven your accuracy? Where's your accurate theorem prediction thingy? That isn't some circular crap and something so obscure and convoluted that you can't even show it to somebody because it's too, it's too complicated.
Theory in all of science. Very, very powerful. Pretty much most of the phenomena, apart from gravity, that we see around us today, we can describe using quantum.
So again, describe how? Describe what? Describe any... No, you don't describe anything. It's just such a lie.
Electrodynamics. And then physicists went further. They said, well, there are other forces in nature trapped inside the atomic nucleus, what are called the strong and weak nuclear forces.
So again, these contrived nonsense forces. So again, even all the way back to Maxwell, so we're talking about 1850, you had this description of charges, and it just makes perfectly good sense if you wanted to say, how do I get two plus charges really close together? Well, the simple solution is to put a negative charge right between it, and you get the plus charges really close together. So you already had the answer. I mean, the obvious answer that, well, there's no controversy or there's nothing difficult in understanding how you can get protons close together if you understand that, well, if I have available electrons, which I obviously do, I mean, where's the missing electrons, right? I mean, if you argued that there's the same number of electrons and protons, you'd have to say that, okay, there's a bunch of missing electrons, right? If you don't concede that the electrons are part of the neutrons, then you'd have to concede you're missing a bunch. Well, if you conceded that the weight of the neutron is being created by the proton, then you'd have to concede that it must have an electron. But anyway, there's lots of ways to deduce the facts that you'd have to combine them, and you just say it's such an obvious solution. You don't need a strong force. You want to get two protons close together, you just stick an electron between them. What's so complicated?
And pretty soon, certainly by the 1960s, they'd combined one of those forces, the weak nuclear force, with quantum electrodynamics.
So there's nothing there. So that's another word. He just made a bunch of statements, but there's nothing there. If you go look and try to find out what the fuck that actually means, it doesn't mean a damn thing.
Bring them two together, and then there's another even grander, more unified theory called the electroweak theory. They didn't stop there. They said there's another force inside the nucleus called the strong nuclear force.
Okay, so we already mentioned that one. So all this is just... So he was going to show us how this has really done something, and all of this is just their hype. There's not anything in the real human universe that shows this having any relevance to anything human in terms of progress, understanding, knowledge, any of that. There's no advancement here at all.
What if we apply quantum field theory to that? And they developed what's called quantum chromodynamics. Then all these ideas brought together by the 1970s.
So that's all spin crap. So we have all these different features that all these tiny little particles have. So instead of them being what they originally understood to be, which one electron is just like all the other electrons, they're just electrons. Now they all have big ears or small ears, and they have noses, and they have eyes. They've given them a whole bunch of features, and just made a mess out of something that was, again, really worked well in understanding the elemental function of the universe, that it's made out of these elemental bits, and all you're really doing is arranging the elemental bits.
In what we call today the standard model.
I mean, it is a checkerboard. It's really simple, and it's just a lot of checkers.
Of particle physics. An umbrella term that describes the physics of...
Right, so the standard model is more, there's nothing to it that anybody could understand as it actually being a model. It's, the periodic table is more reasonable, more discernible, more of a map. You can't make anything out of the standard model. It's just a clump here, a clump here, a clump here, a clump here, there. That's how the universe works. We have these designated pieces of crud, that we call the name, and you're supposed to believe that this boson-y stuff does one thing and this other stuff does something else. And it doesn't mean anything.
As far as we know, all the forces of nature, all the phenomena that we experience, apart from gravity. And today, and certainly for the last few decades, the big challenge in fundamental physics is how do you bring gravity in? That's the last remaining big phenomenon in nature that hasn't come under the spell of quantum mechanics.
Yeah, right. So again, just kind of obvious that from my perspective, gravity is exchanging it's creating momentum, so it must be the same kind of stuff as all the other forces moving the speed of light, that it's capable of causing motion. And so all you have to do is explain the drag issue, I suppose, is the only real obstacle. But the idea of particle gravity does work, creates everything you need it to do. It does exactly what the reverse of a light bulb would be. So if you understood the universe to be full of pressurized little bits moving the speed of light, that pressure would force all the matter into clumps, and so it all makes pretty good sense.
Well, physicists carried on using quantum mechanics. It worked. It was powerful. They developed.
All right, so more like it worked as doing no real work. So it worked only in making their silly model, but it didn't do work in any other way. Fact.
More advanced theories, but not everyone was happy. Einstein, for example, still hadn't quite given up the battle. Despite
So and again, Einstein's half the problem, right? Because he has no right to talk about spooky action when his own gravity theory is just spooky action. It's just some declared mechanism. I'm not going to say what it is. It's just some mechanism. All right, and I can call it a bent something, but there's no point in me calling it a bent something because it's in 3 dimensions and it's really a convergence. So, I mean, he didn't add any value whatsoever. I mean, to connect time and space as if time was a dimension is just nonsense. It's not.
despite being a revolutionary scientist himself, coming up with his 2 theories of relativity, he was reluctant to embrace all the predictions and implications of quantum mechanics. In the mid-1930s, he published a very famous paper, together with 2 colleagues, Boris Podolsky and Nathan Rosen. The title doesn't really tell you much. It just sort of is a question, and it suggests they're not happy with quantum mechanics. But it's famous because it's known as the EPR paper, named with the initials of the 3 authors, Einstein, Podolsky, and Rosen. And from it, within the paper, they outline their issue with quantum mechanics.
Right, so this is the part that's just ridiculous, right? Because, yes, they did all that, and all they got back was convoluted mush as a reply.
Which today we refer to as the EPR paradox. I want to explain this because it comes back again when I talk about our quantum technologies moving forward. So what is the EPR paradox?
Okay, he's going to describe a completely different one than what Einstein actually said, because he's going to use Born's remodification of the argument, which is going to include positrons and other kinds of nonsense that Einstein obviously didn't believe existed.
Well?
You do not need to be liked by everybody. You need to choose your friends and your enemies carefully.
Hell with both.
Imagine, I'm going to simplify it, may not be exactly the way they explained it in their paper, but it's and you can look up online, there's lots of ways of explaining it. But imagine you have some device that produces 2 particles of light, 2 photons, and it sends them out back to back, equal and opposite momenta, equal energies. I've depicted them here as what are called wave packets, photon 1 and...
So whatever. So this is a real thing you can do. Okay, you can take ultraviolet light and you can shoot it into a crystal and you can get 2 infraredish photons out. So this is a real thing. And the idea is they would be inverse. That is, they would be right and left gloves. One of them would be out of phase with the other one and obviously would have a different polarization than the other one. So this is not miraculous.
Photon 2. A particle of light, if it's confined in space, then it's showing its particle-like nature.
So all we're talking about is a frequency, so a compression of, the source material, whatever you want to call, however you want to describe that. But you're basically saying is that you had enough energy, in the original photon, So let's say the original photon was really just two photons, two ultraviolet photons with a very close frequency, and you're just saying that those two are split, separated. And now you have two photons with a wider frequency. So you have the same amount of pieces of quanta moving the speed of light. So again, the whole point is that the whole universe can only be made out of these discrete bits, the little tiny thing moving the speed of light. That's the quantum that should be in quantum mechanics. So the irony is they have a thing called quantum mechanics, but they don't really believe in the quantum. They don't believe that in the universe there is this little bit of energy, this little clump, okay, that moves the speed of light. And the fact is it can give energy to electrons and protons, and it always gives them in these units. Those are the quantum chunks that something can absorb. It can't absorb a half a chunk.
Rather than its wave-like nature. Now we know that light also behaves like a wave. In fact, here on the desk
We know it. Yeah, I don't know it.
is the first volume of the books by Thomas Young, regarded very often as the last great polymath. He just did everything. But
So he was a doctor, as far as I understand. So they should probably call him Dr. Thomas Young. But regardless, he was really big on doing a bunch of stuff with color blindness and lots of other subjects. So you have to give the guy credit. But frankly, this wave analysis shit was junk. It's junk science. Because his own diagrams demonstrate it doesn't work. The math doesn't work. If you put the wave centers in the middle of the opening, which would be where the wave is, the math doesn't work. The geometry doesn't, it fails. The surfaces have to be the point sources, not the center of the wave, the surface. So it shows a huge flaw. If you analyze the water waves based on the surface, you will get the wrong answer. And if you analyze the waves of light based on wave centers, like water wave centers, you won't get the right answer. So they're obviously not the same mechanism.
over 200 years ago, here at the Royal Institution, showed that light behaves like waves.
And it doesn't. Okay. And it's pretty easy to understand how it's different. You can see glaring examples of the difference. The double maxima. The fact that the pattern degrades. It doesn't spread. Lots of things giving it away.
His famous two-slit experiment with light, showing the interference pattern as light passes through two slits. And there are lovely pictures in this book, from the early 19th century, showing that light behaves like a wave.
So there really aren't lovely pictures in the book because no one's been able to redo exactly what his experiments were.
Well, Einstein had showed that light also behaves like a particle. So here I am trying to cover both Young and Einstein's pictures of light. It's sort of a particle because it's sort of confined, it's not spread out from to infinity.
Right, so it doesn't make any sense. It's just this baby talk that somehow a laser beam is waving somewhere and it's spreading, but it's not spreading. It's in a clump, but it's a wave, but it's a who, but it's a what. Yeah, it's just crap. This is garbage, it's science.
But it's also wiggling like a wave. This is what's called a wave packet. Excuse me while I have a drink of water. I recently recovered from a cold. I haven't had any Lemsip today, so that's always a sign that I'm recovering. I'm addicted to the stuff. As soon as I get a cold, I can have Lemsip now.
Limsit. So it must be a British thing. Limsit.
But I just need a sip of water. Right, so photon 1 and photon 2 come out. Once they're some arbitrary distance apart, arbitrary means I don't care. They could be a few meters apart. They could be on either side of the Milky Way.
So the argument is they went to either side of the Milky Way and they never encountered a single other piece of energy in the universe. So no other energy or no other electron or proton was in their way, nothing. They interacted with absolutely nothing.
Relevant. They're far enough apart that you'd hope that they're doing their own thing separately. What if we stick some instrument onto photon 1 to measure its wavelength? Now, if you're measuring the wavelength or the frequency or the color of the photon, that means you're probing its wave-like properties.
Whatever that even means, right? So measured with what? Measured how? How do you measure it without absorbing it? Oh, that's right, you can't.
It's not a particle. Now, if the quantum mechanics, the lesson is that what you get depends on what you measure. If you want to see it behaving like a wave, sure enough, it'll oblige and behave like a wave.
Where? What experiment does that? Right? All the experiments prove that it's a particle, so it always behaves like a particle in the end. It never behaves like a wave in the end. You always see it as if it was a particle. You never see it as if it was a wave. So he can't even get his own story right.
So if you know the wavelength, the color of photon 1, and since wavelength or frequency is proportional to the energy, and you know photon 2 has the same energy, therefore the same wavelength, you instantly know without measuring anything to do with photon 2, you know what its wavelength is. It's behaving like a wave.
So it doesn't make any sense, right? I mean, what are you talking about? When did they do this silly experiment? You already knew what its wavelength was when it left. They both have the same wavelength. So he's talking about phase, I think, and he's just using wavelength instead.
However, we could instead have used a different instrument that measures the position of photon 1. That is, its particle property. And if you know where photon 1 is, photon 2 will also be behaving like a particle in the sense that they have equal and opposite momentum. So by measuring the location of photon 1, we would know the location of photon 2.
They don't have equal and opposite momentum, so again, this is another part of this. Where do you get that part from? Yeah. I mean, I don't know what the odds are you being able to send photons in two directions at exactly the same instant in time. Yeah, good luck with that. I don't think so.
Now, the point here is that...
No, the point here is this is all made up synthetic storytelling. There's no real experiment here. There's just some talk about some magical machine. We did some mechanism, we did something, but there's nothing real here.
As Einstein and his colleagues suggested, sure, when you are measuring photon 1, the way it behaves depends on what you measure, and also you inevitably disturb it as you measure it. You can't reliably say what it was doing before you measured it because you've interacted with it. But no one's touched photon 2. And they argued that they could know or could have known both the position and momentum of photon 2 without interacting with it. How could it possibly have that? It must have had those properties from the start, which seems reasonable.
Right, so he's making the argument against what he's saying. Yes, it seems reasonable to say there's left and right-handed gloves and any of this nonsense that somehow the objects don't know what they are until you take a picture of one of them. Is too ridiculous. That's right. It's just too silly a theory.
The nice example in our everyday world would be, were I to have a pair of gloves, a left glove and a right glove, and I put each one in a separate box, turn my back, and then someone takes one of the boxes away, far enough away from me. I don't know whether I've got the left glove or the right glove, but as soon as I open the box, I see I have the left glove, I know instantly that the other box contains the right glove.
There, that's the answer. You're done.
But what's changed is just the state of my knowledge. It was always the right glove, I just didn't know it. In the quantum world, this isn't what is argued is happening. And Einstein didn't like that. So
this whole, right, I mean, he really is making Einstein seem incredibly reasonable here because, yes, who would like that? It does sound like you're just stretching credulity. You're just making up crap for no good reason. You're saying that somehow there's some feature that something has, and it can be not a feature, but they're not independently randomized objects, that they're somehow connected randomized objects. It doesn't make any sense at all that, yes, one of them will know what the other one, when it stops spinning, the other one stops spinning. That whole idea that I stop something that's spinning here and that stops the thing over there from spinning, that's just too ridiculous.
So their argument was that there would have to be some sort of interaction across, presumably if they were far enough apart, the entire width of the Milky Way galaxy, for photon 2 to know that you're measuring the position of photon 1 or the wavelength of photon 1 in order to change its property accordingly. Surely it can't do that once the measurement's made. It must have had those properties right from the start. That's the only way that it makes sense.
Yes, that's the only way it makes sense. And they didn't have these properties anyway. These properties aren't real properties. I mean, these properties are so elemental. So the frequency of a photon is elemental, right? The polarization is elemental. These aren't complicated things, but they don't have spin. They don't have ears and noses and mouths. They don't have all these other weird, complicated functions. These are all the functions they have. A photon doesn't have any spin. Doesn't have any such thing.
Quantum mechanics says differently. Quantum mechanics says
it has frequency, polarization, and what's the key other one there? The timing thing. Jesus, I hate this. I shouldn't have to search for words. I just said it a little while ago. But the thing about the idea of one being out of sync with the other one. Come on, what's the word for that? Oh, God damn it. Phase. Okay, so that's all you got. You got phase. What is this guy talking about? I don't use PayPal. I don't know what that means. Why is he saying that? I don't see anything in here, any context. You don't use PayPal. What does that have to do with anything? Sorry, I'm just curious. Weird. You don't even have to use PayPal, right? To use PayPal? I mean, frankly, you don't have to have a PayPal account to use PayPal. You can just use your credit card, and it's not a problem. I got to do Aeon for you. Well, whatever that is, but thank you. I don't know what that is. Sorry, you're confusing me, which does happen. You commenters often do that. Yeah, I get you. Okay, so you want to do a donation. To me, the link should work, and you just punch in your credit card number, and there you go. You've made a donation. So, but whatever. It doesn't get worn out. Yeah, I gotta say, there are a couple of people are quite reliable and nice, and I appreciate it. But yeah, I'm not going to get rich. But I'm really not. Don't need to be. I just need to be able to press the video making button. Yeah, that's all I need. Press the button. Press the button. All right, so I'll press the button.
There's photon 1 and photon 2. Neither of them have decided whether they're a particle or a wave.
All right, so this whole idea that they are in some not particles or not waving or not, they just keep making up shit what it is. So they're saying everything about this photon is somehow amorphous and isn't mal-shaped and it isn't a thing and it doesn't turn into a thing until somebody takes a picture of it. It's just so ridiculous.
Not only that, but they are combined together. We say they're quantum entangled. They're described by the same quantum state, a single quantum state that tells us the nature of both photons. A single photon can behave like a wave or a particle, and until you measure it, it's neither. It's both. It's a mixture. The same with photon 2. Forcing photon 1 to make up its mind affects instantly what photon 2 is doing.
Right, so why would anybody reasonable believe this? So it is amazing that all of physics has accepted this theory on the scant evidence. They basically just say so. They say so evidence. I mean, they're really not going to show you anything. They're just going to say, like somebody like Alan Aspect will just say, I did it. I measured this crap. Oh yeah, you did? Do we really know that he did any of that? No. It's just, this is such bullshit. Why'd they wait 25 years to give him a Nobel Prize if it was so obviously a credible experiment proving entanglement? Why did it take 25 years for him to get a Nobel Prize, right? I mean, you got to wonder about those kind of things. I think it's because, obviously, I think there's a lot of people who pretty skeptical still.
Quantum entangled.
Daughter's wedding is in a month. I don't want us to look like Beauty and the Beef.
Darling, relax. We have plenty of time. Just start doing Tai Chi walking.
Well,
I mean, the fake everything. There's just fake everywhere. I can't believe how many, I don't know whether you've noticed in your feed, but I've seen there's like a ton of Feynman channels now. And they all have these fake videos of, just using Feynman's voice, and it's not what Feynman said. And you're just like, this is really just wrong. I mean, it's just wrong that people get away with this shit.
the EPR paper isn't about the fact that you can't know the position of momentum of a particle at the same time. That's what's called the Heisenberg uncertainty principle. Einstein wasn't happy with that to begin with, but he'd sort of come round to the idea by 1935. That wasn't his issue. His issue was that photon 2 must have had this property right from the start. The fact that if quantum mechanics said it didn't, then there was something missing in quantum mechanics. Okay, that it was incomplete. In fact, in the last paragraph, the last sentence in their paper is, well, we have thus shown that the wave function does not provide.
Okay, let's see. The wave function does not provide a complete description of a physical reality. We're left open to question of whether or not such a description exists. We believe, however, that such a theory is possible. So it's, I think, just arguing that why would you jump to this bizarre conclusion when you haven't really investigated the more plausible, simple solution?
A complete description of the physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. The likes of Niels Bohr said, no, let's get on with it. It's not possible. That you can only describe these two photons, however far apart they are, by a single quantum state.
Right. So Niels Bohr said absolutely nothing responsive to the argument, and and people just believe it because they want to.
Date. Well, the paper made a splash. In fact, it made the front page of the New York Times. In 1935, Einstein attacks quantum. No mention of the other two authors of the paper, Einstein and two colleagues. Einstein, by this point, he's the most famous scientist in the world. He's going to get credit for it. But in fact, Einstein didn't write that paper. It was Boris Podolsky who'd written the paper. And Einstein was unhappy, to say the least, that Boris Podolsky then leaks it to the New York Times as well. So
I'm not too sure of that. I mean, I read a biography or two of Einstein's. I don't remember that coming up, but whatever.
He didn't like the idea that it was being publicized in this way, not because he didn't agree with the sentiments of the paper, but it wasn't really his work. Another physicist who sided actually with Einstein was Schrödinger, Erwin Schrödinger, the Austrian physicist. That same year, not long after the EPR paper comes out, He wrote a 3-paper set of articles in Nature. This is where he first describes his famous cat in the box, the cat that's dead and alive at the same time until you open the box to look. Now, Schrodinger's problem wasn't about incompleteness of quantum mechanics. It wasn't about the uncertainty principle. It was about what happens when you make a measurement. How does this thing that can be fuzzy and weird and doing lots of things at once suddenly give you a concrete answer when you look? What is it about?
Oh yeah, what is even looking mean? What does that mean? Could I put a grasshopper in the box with the cat, and now the grasshopper has eyes and it can look at the cat, and so now the cat can't be alive and dead because there's a grasshopper looking at the cat? I mean, the whole thing is just so ridiculous.
Measurements, and so he uses the cat as an example. How can the cat be dead and alive at the same time? What's important in the context of what I want to say is that that's the paper where he first introduces the word quantum entanglement. Verschränkung is what he calls it in German. In fact, a few years later, Einstein writes a letter to another physicist, Max Born, and he complains about what quantum mechanics says is going on in his EPR paper. And that's where he first uses the term spooky action at a distance. Spukhafte Fernwirkung. It's perfect German as far as I'm concerned. Because how can photon 2 and photon 1 be instantaneously communicating with each other? And photon 1 saying, they've just measured my position, you better be a particle. Oh, no, they've measured my momentum, you better be a wave.
So it really wasn't about becoming a wave or a particle, but whatever. It was about some feature, okay, that these particles would share. Some spin or some thing they say these things have, when obviously none of these things have any. They don't have big ears and small ears.
Einstein said, how can that? Surely nothing can communicate between the two faster than the speed of light. But in the quantum world, that seems to happen.
Okay, so another. We just make up some new rules. Break all kinds of time continuity. Who cares?
That is quantum entanglement, and we're going to see later
Yes, I can call you and tell you about an event that won't happen for 10 years.
on how quantum entanglement is helping us in our
Bullshit.
revolution, the technological revolution today.
All right, so it doesn't help anywhere, doesn't really do anything, doesn't make anything, doesn't build anything, doesn't do anything.
Quantum foundations in the 19th... Well, most physicists had sort of resigned themselves to the fact that Bohr had won the argument, get on with it, quantum mechanics works. Einstein was...
So it's just frightening that everybody's comfortable with the wrong side winning for no good reason, and everybody says, great. Yeah, that is hilarious.
somehow the reluctant, old hand who was sort of dragging his feet, not wanting to accept quantum mechanics. There were still very powerful physicists in the 1950s, people like Eugene Wigner and John Wheeler, who were at least prepared to think about, is it completely answered? Are we happy that we understand what's going on in the quantum realm? They were certainly more sympathetic to young scientists who dared, and I use that term sort of quite literally, they dared to argue against the Copenhagen school. People like David Bohm and Hugh Everett.
So yeah, these are really bad examples, frankly, because that's just doubling down on some other woo. They don't fix it with something solid, they fix it with more bullshit.
They came up with alternative theories that would explain the EPR paper, that would explain the cat in the box thought experiment.
There's no explaining it. It doesn't happen. It clearly doesn't happen. Okay, we know there's cause and effect, and there's no way you can ambiguitize it.
That went against the Copenhagen view, which said all that matters are the results of measurement. Quantum mechanics predicts what you will get when you make a measurement.
So that's not true. It's just part of the lie again, over and over and over. They did all these predicting things. So where's their predictions? Where are they? I haven't found any logging of all their predictions. They can't predict the stock market. They can't predict anything.
And you can't say anything about what's going on when you're not looking. Just do the maths. So these were mavericks, outsiders. Another maverick outsider in the 1960s was the Irish physicist John Bell. Now, John Bell famously didn't like the Copenhagen view. He talks of a time when he was caught in the lift with the great Niels Bohr, and he says, I just didn't have the courage to confront him about the Copenhagen view and say I wasn't quite happy with it. Well, many years later,
so then he's going to relate his own story of being in the lift with Bell. But anyway, this whole Bell thing, I guess, is a real. The more you look into it, the more time you waste trying to figure out what Bell was arguing, the more meaningless it seems as an argument.
In the late 80s, I was caught in a lift with John Bell. This was at an American...
I mean, this all ends up being about polarization of light and the percentage of the light that you can recover by putting a filter in at some other angle. Okay. Probabilities.
Physical Society meeting in Baltimore in 1989. I was finishing my PhD and looking for postdoc positions in America. And I'd just come out of a talk on quantum mechanics given by someone who clearly was promoting some new idea which I thought was nonsense. And I got in the lift with John Bell. And unlike John Bell, he didn't have the courage to confront the great Niels Bohr. I had the courage because I agreed with John Bell. So it was easier. So I said, that last talk, I knew he'd been in the talk as well. That last talk, yeah, and he said, yeah, I agree with you. Has he not heard of such and such? He obviously doesn't understand quantum mechanics. So I felt very pleased that John Bell and I both agreed on this matter.
Like in telling this story, he can't tell us who the physicist was that was making the story. You'd think you'd really remember who that presenter was, and he doesn't have the courage to tell us what that is. Just showing some of the bullshit.
Long before that, in 1964, John Bell had come up with a theorem which no one really had thought possible. It was a theorem that would essentially work out, was Bohr right or was Einstein right? This is... there's such exaggeration. The most profound discovery in science. I mean, just amazing bullshit. Just bullshit. Often regarded as the most profound discovery in science. He said, if Einstein's right, if nature is local, now local means you can only interact with things close enough to you, and if it's far away, then you need some time before you can influence it. Time, the fastest you can get to it is...
So none of this has anything to do with the experiment, so I don't know why this time crap is coming up again. This doesn't have to do with distance and locality. It has to do with whether or not there's actually a real randomness to what glove it is. Yeah. But anyway.
By sending a light signal. And you can't interact with something instantaneously if it's too far away. He said, so if Einstein's right and nature is local, then there's a formula that says there's only so much that's like, for example, the EPR photons, there's only so much those two particles can have in common, given that they were both at a single origin. They started off together. A left and right glove, for example. They can't then change what they're doing when they're far enough apart unless they have enough time to tell each other what's going on.
So again, this time thing doesn't really have anything to do with it. So I don't know why he's using that as an example. But whatever.
He said, this formula, it was formed as an inequality. Four other physicists, Clauser, Horn, Shimoni, and Holt, called the CHSH inequality, put it in a nice, neat mathematical formulation that allowed experimentalists to go away and check it. Once and for all, can we shut Einstein up?
Start doing this with your dog.
Yeah, and who believes it? Yeah, not me. But anyway, okay, so maybe we'll call that enough of this for now. And maybe we'll come back to it, blah, 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 and such. Yeah, what do you want, Zach? Gary, will you do some reviews on the... What does that mean? Parapsychology? Why? What do I don't even know what parapsychology is. Well, what the hell is that? Yeah, sorry. Monads and solitons? No, I won't do any videos on that. I mean, in some respects, physics is the only subject, and it's just this understanding of how the evolution of these mechanical bits through time in a universe, and and that what we are is, we're nothing better than big clumps of bacteria with an agenda. Remote viewing, no, I'm not going to bother with any of that crap. Yeah, if you think people are doing any of that, then you're really kind of a silly person, frankly. It's not happening. We don't have any special brilliant functions. We're not X-Men. We're not mutants. Don't happen. It's not real. And such. It's been proven over and over again. I mean, nobody can, when tested, nobody can demonstrate any of these capacities to read anything's mind or to see cards or to predict anything or any of it. So, no point. But anyway, enough of that. Alright, so I guess I will call it a video and such. So, till the next time, and such, and so forth, and whatnot. Yeah, I guess